curves and their Fukaya categories part 1.
Okay, thank you very much. So in this series of talks, I'm going to try to focus on revisiting mirrors of curves and the Fukaya categories. And so this is in some sense the continuation of the last few talks I've given here about joint work with Mohammed Abouzaid, which has still not appeared. So my hope at this point is if we die of old age without this being written, there will be enough videos of these talks to reconstruct the arguments. So let me start by just giving some context, and then I'll try to explain the general plan. So the point is, it starts from a construction of mirror symmetry for hypersurfaces. Mirror construction. For a hypersurface, let's call it H, inside some ambient variety V, which in, first example might be just the algebraic torus. I will write C star to the n. But really, since I'll be doing algebraic geometry here, you should think of this maybe as being over a non-Archimedean field instead of complex numbers. But this could also be a toric variety, or in fact, abelian variety, and so on.
What does and so on mean?
Conceptually, in paper number large n out of many unwritten papers, anything for which we understand mirror symmetry well enough should do the trick. In particular, you can start from somebody like this and get complete intersections. We already know how to do complete intersections. And then I think maybe I don't have any concrete and so on to offer. And so the plan here is to discuss how to understand the B model, the algebraic geometry of H, so things directly of coherent sheaves of H, versus some Fukaya category of a mirror. And so the overall plan for the series of talks, I'm going to switch to black, is first remind you of the geometric setup. What is the Landau-Ginzburg mirror to this situation? Then I will try to explain something about fiberwise wrapped categories and how one can get to an understanding of homological mirror symmetry in this setup. So this is this joint work with Mohammed that's not really in progress at this point. And then after that, I want to explain how one can recast this in ways that might look more like mirrors of curves, in the case of H being a curve inside the surface. And so I want to start thinking about possible reformulations, such as going down using mirror periodicity, working in the fiber using tropical Lagrangians, and that's going to be hopefully the topic of the last talk. I was going to say working on the critical locus of a superpotential. So in particular for mirrors of curves. So the mirror of a curve viewed, say, as a hypersurface in some surface, initially will start out being a three-dimensional Landau-Ginzburg model, and we'll look at three-dimensional Lagrangians in there and their Floer theory. And this works very well for proving statements, but it doesn't feel like you're working on a curve. And of course, it's because you're working on the abelian space secretly. And so for mirrors of curves, now instead this will amount to working on some trivalent configuration of maybe CP1s and complex planes, and trying to do Floer theory for Lagrangians that look like trivalent graphs drawn on these. And that looks a little bit science fiction-y, which is not very surprising given that one of the people in this project is Ludwig. But I believe I can make some precise statements. This is also something that Efimov attempted to explain at last year's conference, and that I've attempted to explain at a couple of other places since, and so far we've always failed. So this is, maybe third time is a charm or something. Anyway, so that's the general plan. And so for today, I want to start again with things that are basically very similar to talks you may have seen me give 2 or 3 years ago, but as a way of eventually getting towards some new territory. Okay, so let's start with a geometric setup. So I will not say the word complete intersection anymore, for everything would work there. And instead I will just worry about, I have some n-1 dimensional hypersurface, which has some defining equation. Terminology will be F, usually for that. Inside some variety V, which could be C star to the n or a toric variety. Or, again, abelian varieties work. That's the thesis of Cannizzo. I'll mention that from time to time, but my main examples will be these. And so what we want to do with that, so to be honest, this is actually either a degenerating family of complex hypersurfaces near the tropical limit. There's going to be some parameter t, and as t goes to 0, the equation degenerates and it looks more and more singular. Or the whole thing should be done over a non-Archimedean field. Maybe a Novikov field or something like that. Okay. So let's say that we have a hypersurface defined by some equation. If I'm in C star to the n, that's just going to be a Laurent polynomial, or rather a family of those with a parameter t. In a toric variety, I can still do the same, thinking of my toric variety as a compactification or partial compactification of the open torus. So it has a defining equation, which is a finite sum. There's a finite subset of the lattice of some coefficients, C sub alpha, times t to the some number rho of alpha, times x to the alpha. Okay, so this is a Laurent polynomial, or a family of those as t goes to 0, or a non-Archimedean Laurent polynomial if I think of t as a formal variable that's part of my coefficient field. The C sub alphas you can think of as just being numbers. They're kind of irrelevant, except for the whole story to work very well, they should actually be precisely tuned to be elements of a Novikov field that equal certain mysterious Gromov-Witten generating functions of a mirror. Let's just say these are constants, that I will not tell you what they are, but if they're well chosen, then everything becomes true. Okay. So given such a Laurent polynomial, you're supposed to look at the tropicalization of f, which is a function I will call phi. It's a piecewise linear function from Rn to R. And it's going to be a max of linear functions, which are just alpha times c minus rho of alpha. So these measures, roughly speaking, whichever alpha accomplishes the max in this will be exactly the dominant monomial in this expression at any given point. All right. So the mirror construction of this can be found in many places. So the one I was most directly involved in was with Mohammed and Ludmil a few years ago, and basically justifies this by the Strominger-Yau-Zaslow perspective on mirror symmetry. But there's earlier indications of this in Horry and Waffa in the prehistory of mirror symmetry, in Patrick Clark's thesis, also work of Chan, Lau, and Leung around the same time as us, and probably I'm forgetting other references. So the idea is to define the toric Calabi-Yau n+1 fold Y with the toric Kähler form omega by a moment polytope. Okay, so it's going to be the toric variety with moment polytope. Delta sub y is everything in Rn+1 which lives over the graph of the tropicalization field. And okay, so this is an open, this is non-compact polytope in Rn+1. Then next beast of interest is a monomial on this with exponent vector 0, 0, 0, 1. So this is really that points straight up. So maybe I should start doing some examples. So our running examples will be very modest, but it's kind of hard to draw pictures. So the main running example will be the case of a pair of bands defined by x1 plus x2 plus 1 equals 0 in C star squared. Then the tropicalization of this looks like the max of 0, C1, and C2. And now if you imagine the graph of this piecewise linear function, and what sits above that, that's congruent to a standard octant in space by a shear. So this gives you, in fact, that y will be c cubed, and W0 will now be minus z1, z2, z3. The toric monomial corresponding to a vector that points straight up vanishes to order 1 on each toric facet of this polytope. In general, this is the monomial which vanishes to order 1 on each divisor. Each toric divisor. Okay. And so the claim is that these are mirror to each other. In fact, there's a generalization of this to higher dimensional pairs of pants. The n-1 dimensional pairs of pants is given by sum of variables plus 1 equals 0 in C star to the n. And its mirror ends up being C to the n plus 1 with minus the product of the coordinates. Okay, so the claim first is that y0 is mirror, in some sense, to, I will say, to a hypersurface in C star to the n. And if you didn't start out in C star to the n, just intersect with the open torus is what I mean for now. Okay? And, all right, so another example of that, just, for saying something slightly less trivial, I can look at a free punctured elliptic curve in again C star squared, given by the equation x1 plus x2 plus t over x1, x2 plus, and here I will do a cop out, I will write 1, but true Gromov-Witten enthusiasts should know that this 1 is actually a 1 plus, I think there's an 8 and something and something. It's some generating series of local P2. Anyway, it's a constant term. Okay, so this is actually a free punctured elliptic curve in C star squared, and the corresponding tropical thing looks like, well, what you would imagine given the picture I've drawn. So in the center is where the constant term dominates. I have 0. Here I have C1, I have C2, and here I have minus 1 minus C1 minus C2. And so now if you take the things that, the polytope that's over the graph of this function. That's again some open thing in free space with one triangular facet and a bunch of unbounded facets. And after a shear, you see that this is in fact the total space of O of minus 3 over P2. So this one corresponds to Y equals the total space of O of minus 3 over P2. And W0 is again the monomial which vanishes to order 1 on each of these 4 divisors. So it's in fact the product of the 4 natural coordinates you can think of in this space. Okay. So, a couple of remarks about this. I know I still owe you the statement of what is the statement when I'm not in C star to the n but in a toric variety. That will come up, okay? First remarks first about the geometry of this. So the smooth fiber of this monomial W0. Again, if I'm thinking of a Landau-Ginzburg model, for me that will mean I will think of this, since I'm going to do symplectic geometry in there, I have this scalar manifold Y, and I'm projecting it down to the complex plane by this function W0, and I will be interested in Lagrangian submanifolds of Y that sit in a nice way relative to W0. Okay, we'll get more on that later. So in particular, it's interesting to know what are the fibers of W0, what are the level sets, what are its singularities. Okay, so the smooth fiber of W0 is in fact always isomorphic to C star to the n. That's a basic fact of toric geometry. Setting a monomial equal to some non-zero value on a quasi-projective toric variety tends to do that for you. What else? The singular fiber so the zero level of W0 is in fact the union of all the toric strata in Y. So it's a union of toric varieties, which you can see pictorially on these pictures just by looking at the various regions delimited by your tropical hypersurface and viewing each of these as a moment polytope. Here it's 3 copies of C squared, the coordinate planes in C cubed. Here it's a CP2, and 3 of these O of minus 3 over P1s, which are the coordinate planes of coordinate axes of the P2. Okay. The critical locus of W0 is the union of the codimension 2 strata. So for curves in C star squared, with a maximal degeneration, so under the assumption that I've chosen my coefficients generic enough for Y to be smooth, this is a trivalent configuration of P1s and Cs. And so, over the course of the lectures, I'm going to try to bring the geometry of these mirrors, symplectic geometry, down from the total space, eventually all the way to here, with well, a few gaps in our understanding. But okay, so the other remark, because there are other competing candidate mirrors, is that in simple cases, in simple examples, such as these two, Y is in fact the total space of some line bundle, in fact always the canonical bundle, over some lower dimensional toric variety. Let's call it Z. Okay? And W0 is a product of the fiber coordinate, and this is a section of the anti-canonical on the base. Okay. For example, well, you can do this here, say, by splitting off one of the variables, and here, similarly, you can split off the fiber variable. Maybe I should have told you what's the W0 here. It's U, Z0, 0, Z2, where these are the coordinates in the base P2, and this is the fiber coordinate. Okay, so in this case, we expect, so Orloff has a result which extends Fourier periodicity to categories of matrix factorizations. And Orlov's result says that the derived category of singularity, so now I'm temporarily making this the algebraic side of YW0, is in fact equivalent to the derived category of coherent sheaves of the zero set of this section sigma inside Z. So this gives you a smaller, nicer candidate mirror in these examples. So then we expect that in fact sigma inverse of 0 inside Z is a smaller non-Landau-Ginzburg model, so sigma model or something, mirror to H. Usually singular. So for example, in the first example I had, for the pair of pants, C cubed is the total space of a trivial line bundle over C squared, and this potential is a fiber coordinate times the product of the two base coordinates. So I can look at Z1, Z2 equals 0 inside C squared, a nodal curve. Okay? And so this is also a valid mirror to the pair of pants. It has the advantage of being much smaller, one-dimensional. It has the drawback of being singular, which symplectic geometers don't usually lack. That one corresponds to Z0, Z1, Z2 equals 0 inside P2, which is a singular cubic in P2 consisting of the three coordinate lines. You could also do this, of course, for bigger examples. There's nothing to prevent you from working with higher genus curves. They have mirrors in this kind. But then, in order to see Y, to make Y end up being just the total space of a line bundle, you have to actually take a stacky mirror by taking the non-maximal degeneration. And stacky things are even more taboo to me than just like simple singularities like that, so I will not go there. But in principle, there are mirrors of this kind to curves. Okay. All right. So now, okay, that was inside C star to the n of the algebraic torus. Instead, if I'm in a toric variety, maybe I need to assume V to be Fano, so let's do that, because that's, so it's still defined by an equation like before. You can think of it as a Laurent polynomial in some coordinate choice. But now this is likely to be a section of some line bundle, L or O of H, and probably use O of H most of the time because there will be way too many L's already once I have Lagrangians. Okay, and of course the convex hull of a set of exponents that appears should match with the Newton polytope of this line bundle. So then, the candidate mirror is still the same space Y, but the superpotential has additional terms. Okay. So this is the same Landau-Ginzburg variety. W0 is still the same as before, but now I will have additional terms. One of them for each ray of a fan, sigma V, of the toric variety V. So basically, if you prefer, for each compactification divisor that V has acquired compared to the algebraic torus, there will be one extra term in here. I have to attempt to give a formula without being very precise. It's a sum indexed by the rays of a fan, of the generators of the rays, I should have said. There's some formal variable big T, which is actually a Novikov parameter on the other side. Some power of that times a monomial whose exponent is basically determined by these rays. This lambda, so this is like in z to the n, and this is an integer which is determined by the line bundle L. You know that each line bundle comes from a piecewise linear function on the fan, and this is where it comes from. Okay, this definition is impossible to process in the amount of time I'm going to give you. So let's just agree that there's extra terms, one for each compactification divisor, and I'll just show you a couple of examples. So, first example. If I take my pair of fans in C star squared and compactify it to a line inside P2 instead. Okay. So this is really just P1, but obtained. If I think of removing, this is really a pair of fans compactified by adding 3 points to it. So then this prescription says the mirror is still C cubed, with a superpotential, which is, so the first term is as before. And then there's terms for each of the compactification divisors, which end up being Z1 plus Z2 plus Z3. This is and you can ask, well, what's going on here? It's debatable how you should think of this, but one possible way to convince yourself that this is not completely nuts is that this still has two isolated non-degenerate critical points with the same critical values as the usual mirror of P1. That's at least slightly reassuring. The other one is if I take my elliptic curve from before, from example 2, and I compactify it into the toric variety whose moment polytope is dual to that of P2. This is the simplest toric variety inside which this equation wants to become a section of a line bundle. Then the mirror of that will be the total space of O of minus 3 over P2 again. Let's call the coordinates U, Z0, Z1, Z2. And now the superpotential will be, so still the old term, negative U, Z0, Z1, Z2. This is W0 plus T times U times Z0 cubed plus Z1 cubed plus Z2 cubed. And this is W sub V. So what this amounts to, this one now is actually Morse-bot. See, this is actually U times the defining equation of a smooth elliptic curve in the Fermat pencil, which deforms the singular one. And of course, that elliptic curve is the classical mirror of this torus. Okay. One last example before we put everybody to sleep. If I look at a genus G curve of genus at least 2 inside a toric del pezzo, then you get something which is a threefold on which the critical locus is a trivalent configuration of 3G minus 3 P1s meeting in 2G minus 2 points. Okay, so for example, if I take a genus 2 curve and I take a large complex structure limit which kind of stretches it into 2 pairs of pants. In fact, that's a lie because the setup that I'm here, I'm going to stretch into more pairs of pants and caps where I intersect the divisors, will be mirrored to, well, I'm going here a picture of complex. Since I'm going to do eventually symplectic geometry here, I should probably draw the real picture. This is going to be 3 spheres meeting in 2 points. And near each of these points, this looks a lot like the coordinate axes in C cubed, and as a critical locus of x, y, z, z0, z1, z2. Okay. All right. So, just for the written record, there's also a version in abelian varieties. If you want to learn about that, this is not where you will learn about it. Instead, you should look at Cannizzo's thesis. And there's a version of this for complete intersections. And it works just the same as this, except now you have a mirror which is a toric variety of dimension n plus k, if h is dimension n minus k inside v of dimension n. And W0 now has k different terms. This hopefully will be in our paper with Mohammed somewhere. Okay. All right, so now I need to start talking about what HMS, what homological mirror symmetry says for these examples. Any questions before that? I think the things I'm looking at are, oh, you mean on these mirrors. I will have to tell you, so I'm using the toric structure to know how to deal with issues of holomorphic convexity. I mean, that's going to be part of the explanation of what is the Fukaya category of these things. That's right. I mean, essentially, there's a narrow band of examples where the mirror is exact and affine, and you can just use techniques like sectors or microlocal sheaves or skeletta to get there. But most of the examples we care about are not going to be exact as mirrors. Now, they're convex at infinity. It's just a matter of getting the Lagrangians to cooperate with that to make Floer theory well defined. And I'm sure there's a lot of different ways of doing that. Mohammed and I have embarked on one particular way which seems to work well for this purpose. So that's the one I will use. Okay. So, all right, so homological mirror symmetry relates to different things. One, it relates the wrapped Fukaya category of the hypersurface H, or its usual Fukaya category if it's compact. Two, derived category of singularities of a mirror, or DB-co of the smaller thing, sigma inverse of 0, via Orloff's results in the case where this is feasible. So this case has been well studied, and so I will not focus more on it in here. I'll just put a few names. So for curves in C star squared, there's the infamous 5-over paper, but then the one I like best is Heatherly's thesis, which does this in a way that's very natural for pair of pants decompositions. There's also work of Nadler and Gamage and Shende. So this is like going to higher dimensions, but using microlocal sheaves, which now using the language of sectors we know are the same thing anyway. So that's probably okay. And there's also work of Lekili and Polishchuk that I believe Sasha will tell us more about tomorrow. Okay. probably many others that I'm forgetting. So apologies to everybody who made the list this time. But so the direction I want to focus on in these talks is the other one, relating coherent sheaves on H to the Fukaya category of the Landau-Ginzburg model Y, W. So one answer, which actually works well when it works, is using micro-local sheaves. So Nadler has a very nice paper for pairs of pants this way. Or sectors, notre pardon Shende, this works when Y is exact, which is rarely the case in our examples. Conceptually, sectors can probably be pushed beyond to non-exact setting, but this is not the place to speculate on that. So the next thing the one I want to focus on today actually is going to be this so-called fiberwise wrapped Fukaya category, which Mohammed and I have been holding up for a while. So this is what we will discuss today, but I also want to point out other options that we will go towards. So one is to look at the Fukaya category of this smaller singular mirror inside Z when such a destabilization exists. And of course, there's a question of what do we mean by the Fukaya category of something that's always going to be singular in real-life examples. And this is relating to work in progress of my student Maxim Jeffs. And then the slightly more pipe dream version of this is to work directly on the critical locus of W in a suitable way. And so the advantage of this is, you see, the mirrors we construct, this space Y, depends very much on the ambient space V. And that's kind of unavoidable when you see the structural features of mirror symmetry for these Landau-Ginzburg models. V is everywhere. Well, not here. In principle, you can think of, in the abstract, a mirror correspondence between such pictures and such pictures. And that you don't need an ambient space for that. So that's kind of motivation for trying to understand this. And so this will be where we try to get to at the end. Not today. Okay, so, all right. So I think I've postponed enough. Now it's time to kind of define the Fukaya category. At least say a few words about how you would define it. Okay, so this is an ad hoc construction for the class of toric Calabi-Yaos that we end up with. I think it can extend a little bit beyond, but not much further beyond. Clearly, more robust ideas like sectors probably would do it. Okay. So the objects of this thing will be properly embedded Lagrangians submanifolds L inside Y, which are, so first thing I want to do is unobstructed, which means don't bound any holomorphic disks. Okay. This is like a usual sanity assumption in Floer theory. With extra data, such as spin structure, grading data, local systems. If somehow you still want to have some disks in there, maybe bounding cochains, things like that. But for now, main construction doesn't need any of that. And here's the interesting question. What class of Lagrangians? So I will call that monomial admissibility, following the language of the work in Andrew Hanlon's thesis, with respect to the various monomials that appear in this superpotential. So remember, we have a main monomial W0, and then we have, if we are not just in C star to Vn, we have extra terms coming from the compactification divisors. So monomial admissibility is the requirement that when these monomials become large, rather for each of them in a suitable subset of Y, we will have control over the argument of that complex monomial. Say we will require it to be real positive. Okay, so the classical way to define the Fukaya category for a Landau-Ginzburg model that works very well for Lefschetz fibrations, for example, is to look at Lagrangian submanifolds with image under the superpotential fibers over some arcs. And one could try to do that here, but somehow it kind of breaks down at some point with issues of compactness at infinity and so on. And it turns out that it's actually much nicer once you have that language of monomial admissibility. It kind of really brings out a lot of things that you can do with it. So this, instead of looking at the sum of all the terms in the superpotential and putting conditions on the argument of that, actually basically works with, if you want, some kind of semi-tropical approximation of a potential by requiring that whichever monomials are the largest in a suitable sense are constrained to be real positive or to have a fixed argument. Okay? So to spell it out in this case, let's start with W0. When the norm of W0 is, say, bigger than 1 or some fixed constant, we require that the argument of W0 on L to be locally constant. And moreover, that constant is, say, somewhere in the right half plane. So W0 goes towards, say, east infinity. Okay? So if you prefer, that means that W0 over L is in a union of radial arcs outside of a unit disk. And these arcs are actually in the right half plane. Maybe I can start with forthcoming example. So this is going to be a running example, which I can't, anyway, I will build it as we go. Okay, so in the mirror of a pair of pants, let's look at the following thing. So we know that over the origin we have a union of the three coordinate axes. Everywhere else we will have C star squares. And so here we have a union of C star squares. And everywhere else we have C star squares. So I will look at Lagrangians in practice. The ones I will care about live over some kind of U-shaped thing, which has two radial arcs. And that's why I didn't want to set this argument equal to 0, for example, because I need actually two different values for this to work well. But so at infinity, the argument of W0 is constrained. What this buys me for free is a nice maximum principle or open mapping principle or a combination of both for projection under W0. Things can't escape too far out at infinity in the W0 direction because, well, there's just no non-constant holomorphic curves with boundaries on these radial arcs. So that's the first part. But then you can ask, wait, but what about in the fiber in C star squared? So there's more. This is like one of the monomials that can appear there. Okay? So next, the other monomials. So recalling that the fibers of W0 are in fact copies of C star to the n, outside of a compact subset of each fiber, we find a finite open cover, U sub mu, and a collection of toric monomials, Z to the mu. So where do these monomials come from? If V is compact, we take exactly the monomials in W sub V. If not, compactify to some V bar and take the terms that would appear in that one. So what I mean by that is, okay, if I'm just looking at a pair of pants, this is the mirror, there's no other terms. But to gain control fiberwise over the infinity in C star squared, I will think that maybe the pair of pants, remember, so this was in C star squared, x1 plus x2 plus x1 equals 0. This might want to compactify to P2. And then I said that inside P2, there were going to be these monomials, Z1, Z2, and Z3, that were going to appear as extra terms in the potential if I did that compactification. So this is the most natural choice to use for the pair of pants. In general, you look at basically, what is the convex hull of the set of exponents that appears, and you take the dual polytope and you take the rays of corresponding to that. Okay. So we have a collection of monomials, and now the rule that we will make is that fiber-wise, when Z1 is large enough, then we want, say, Z1 to be real positive in this open set corresponding to Z1. So when I go to this part of the fiber, Z1 has to be real. When I go to that part of the fiber, Z2 has to be real. When I go to that part, Z3 has to be real, and there's an overlap. So there's a region where two of these have to be real at the same time. Okay? So the requirement, so there exists such a finite covariant collection of monomials such that the argument of Z to the nu restricted to L intersection mu sub nu is again locally constant. And here actually it's okay to prescribe a value, so we can say prescribe that it's 0, for example. Okay? So an example of a Lagrangian which always satisfies these things inside the fiber is to take what I will call L0, which is the real positive part, r plus squared in C star squared in this case. All the variables have argument 0 when I'm here. And now the next question you can ask, so some of you may know that to build a Lagrangian in a symplectic fibration, which fibers over an arc, it must have the property that you have a fiberwise Lagrangian, and then how it must evolve has to be by the symplectic horizontal distribution given by the symplectic orthogonal to the fiber. So the question you may ask is, does parallel transport preserve monomial admissibility? The answer is in your dreams. But the statement is there exists a toric Kähler form in the cohomology class that you want that will have this property. It's just not the most obvious toric Kähler form. If you do the parallel transport calculation for C cubed, you find that the asymptotics are okay, that the argument of these variables tends to 0 when they become large. But to have a good control by maximum principles and open mapping principles on holomorphic curves, we don't want it to tend to 0. We want it equal to 0, and it's cheaper to change the Kähler form than to worry further about maximum principles. Okay? That's what you get when you don't have analysts on board on the team. All right. Okay, so this is the shape of the Lagrangians. And really for mirrors of things in C star to the n, these auxiliary monomials and so on are just a technical means of controlling maximum principles. When you are now working inside a compact toric variety V, this in fact is exactly the condition that tells you that inside each fiber of W0, you will get an admissible Lagrangian in the mirror of V. Okay, I will get to that at some point, but maybe I should start planting the germ of the idea. These fibers are not just C star to the n's. If you equip them with these extra monomials W sub V, they become the toric mirror to the toric variety V. And this is maybe now why these conditions make sense. Okay, did I put Andrew Hanlon's name in there? Yes, okay. All right. So next we need to talk about Hamiltonian perturbations. to define Floer intersection theory between these objects. To define morphisms between Lagrangians, you're supposed to do their Floer intersection theory. And here, these guys are non-compact. We need to put them in some prescribed position at infinity before we intersect them. So given an admissible L, there's a flow, an autonomous flow, so you can do it for all times and it composes nicely, L sub t, of things which are Hamiltonian isotopic to L and admissible, so they remain among reasonable things. The flow, what it does is to increases the values of the arguments that have been prescribed. At infinity, or if you want, in the prescribed regions. Okay, so we have all these toric monomials whose arguments have to be locally constant at all the ends of our Lagrangians, and we just want to change the values of these constants. So what this does is, in the base, it will take this curve and it will push it until the radial ends have moved past where you were. And of course it will keep pushing. This is just a flow that you can do for ultra large times. But after that time when they have crossed, nothing else happens for this pair of Lagrangians. And in the fiber, same thing. And now I reveal my lack of artistic skill. This is going to look a lot like wrapping at infinity inside the C star squared. Now you want to deal, okay, so how does it increase? For W0 and for the terms which appear in the superpotential. So the role of the superpotential is to slow the wrapping. These are the directions in which you do not want to wrap. You want to do small perturbations, like in Fukaya-sidal categories. So the argument will increase in a bounded open interval. Let's say to fix ideas, minus pi over 2, pi over 2. Okay. Cannot go all around, no wrapping. For the other monomials, the ones that only came from this fake compactification that we wanted to consider, we let the argument increase to infinity, which means we actually wrap our Lagrangians. Okay, so this is why it's called fiberwise wrapped, because the third example is this pair of pants, where you push only a little bit the W0 direction, but inside the fiber, you actually look at fully wrapped Floer theory in C star squared. Okay, and so now having said that, we define term of L0, L1 to be the direct limit as t goes to infinity of a Floer complex of L0t and L1. So these things have natural continuation maps between them, induced by continuation elements between L0 and its push-offs at successive times. And basically what, okay, maybe this is like the end characterization. The formal thing to say is that you localize with respect to the natural transformations induced by these continuation elements as you go along the flow. Anyway, the point is you make all of the push-ups of L isomorphic to each other by brute force, and you declare that the correct position for calculating is when the first of the two has been pushed off a lot in the positive direction. Questions? I think this begs for examples, especially since you need to get to an example at least before we end up the time. So, small observation is that these fiberwise wrapping Hamiltonians are exactly those which appear in Hanlon's thesis on families of mirrors of toric varieties where he shows how, by pushing things around, you can actually implement mirrors to tensoring by line bundles. For mirrors to tensor by O of D, where D is D bar minus V, the compactification divisor. So in some sense, if you don't do the wrapping, but just the infinitesimal pushing, you will end up with a statement of mirror symmetry inside V bar. And now to go back to V, you need to localize with respect to multiplication by the defining equation of the compactification divisor to restrict to the complement of that and land back inside V. Somehow there's justice in how these things fit together. So the localization corresponds to going from dB of V bar to dB. Okay. So, okay, maybe calculation on this example. So we'll go back here because I want to discuss this example. So example, so let's call L0, this Lagrangian, big L0, this Lagrangian inside C cubed Z1, Z2, Z3 by parallel transport of L0, which is R plus squared in C star squared, along a U-shaped thing in the bits. Okay, so if you try to calculate the endomorphisms of L0, so you have to push L0 in the positive direction, and you see that in the base there will be two intersection points, one here and one here. Inside this fiber, I will see, so this is L0, this is L0T. So inside this other fiber here, I also see, I'm going to overlay things anyway. I see something that looks kind of the same. I mean, there's a little bit of monodromy taking place around the central fiber, but in this example, it's barely noticeable once you wrap enough. And so there's going to be two sets of intersections between these Lagrangians, one in this fiber, one in that fiber. Inside each of these, it looks like the Wrapped-Fleur homology of L0 with itself. Maybe I should say the Wrapped-Fleur complex. It's the same thing in this case. Direct sum, two copies of it. But these guys here live in degree 0. These guys here live in degree -1 if you keep track of the gradings. Okay. And so now the Fleur differential on this. So I didn't say that the structure maps are now just given by ordinary unperturbed Fleur theory. Count holomorphic curves with boundaries on these Lagrangians. So you want to look for holomorphic disks with boundary on these two. Nothing happens inside the fibers. So the only interesting configurations are things which are holomorphic sections over this region in the base, with boundaries on L0 and its push-off, and asymptotic to intersections here and here. And so the claim is that the differential can be calculated explicitly because given an intersection, this section has to pass in exactly one point through this union of three C squares, and there's three possibilities it can choose, and then that will determine the output intersection. So the claim is this is going to be multiplication by 1 plus x1 plus x2 from, sorry, I should have said first what this is. Okay. So the self-wrapped Fleur cohomology of R plus squared and C star squared is Laurent polynomials in two variables. Okay, and the connecting differential is multiplication by 1 plus x1 plus x2, so that indeed in cohomology, will look like Laurent polynomials in two variables, quotiented by the ideal generated by 1 plus x1 plus x2, which is exactly the endomorphisms of a structure sheaf on the pair of pants. Okay. And similarly, and with this, similarly for any hypersurface in C star to the n, L0 obtained by U-shaped parallel transport of L0, which is just the R plus to the n, corresponds to O sub H, in the sense that the endomorphism algebra of this object in the fiberwise rat category matches exactly the ring of functions of this affine hypersurface. And so this gives HMS once we know that L0 generates. And that's actually, I don't know for sure the answer to that. So maybe it's known by now, but not quite known to me with certainty. Okay, so next time I will tell you what happens in the case where this was in a toric variety V, and then we'll look more at the structural properties of these diagrams of functors involving them, and we'll start on our way to reformulating this in slightly more pleasant ways. And then on Wednesday I will jump to trivial things. Thank you. Yes, Maxim.
Do you understand one can reformulate this to have some function on the variety which is goes bounded below, but in some direction goes to plus infinity, in some direction is bounded, and we apply this function to Lagrangian on which is goes to infinity. Is it possible?
You mean as the wrapping? Yes. Yes. There is a wrapping Hamiltonian of this form.
So this is kind of bounded in certain direction.
Yes, exactly. So it's a Hamiltonian that goes to that is proper on this. I mean, or, you can think of it as a collection. Here it's easier to think of it as a collection of things, one for each monomial, but you could combine them into one. And then there's an extra technical condition, which is basically that DC of this Hamiltonian has to vanish at infinity on the Lagrangian. This is the analog of the condition of having constant argument for the function of which this is the norm. And then there is a maximum principle at the boundary. So it's yes, you can reformulate it like that.
More questions?